Welcome to Scapple TV.
Today, humanity takes a step closer to understanding short-duration gamma-ray bursts, building a better battery, and have we discovered gravity waves? This week on Nerd News. Gamma-ray bursts are mysterious flashes of intense high-energy radiation that appear from random directions in space. NASA's Hubble Space Telescope has provided the strongest evidence yet that short-duration gamma-ray bursts are triggered by the merger of two small, super-dense stellar objects. A team of researchers led by Niall Tanvir of the University of Leicester have used Hubble to study a recent short-duration burst in near-infrared light. The observations revealed the fading afterglow of kilonova explosion. The Hubble observed the light of a fading fireball produced in the aftermath of a short gamma-ray burst. A kilonova happens when gravitational radiation, or tiny ripples in the fabric of space-time, begin to dissipate, causing the two objects to sweep closer together. In the final milliseconds, as the two objects merge, they emit highly radioactive material. This material heats up and expands, emitting a burst of light. This powerful kilonova blast emits as much visible and near-infrared light every second as the sun does every few years. This discovery about short-duration gamma-ray bursts helps us to understand the origin of many heavy chemical elements in the universe, including gold and platinum. Kilonovas are predicted to form such elements in abundance, spraying them out into space where they could become part of the stars and planets. Secondly, the short-duration gamma-ray bursts are also expected to emit intense gravitational waves, first predicted by Albert Einstein. Speaking of gravity waves, a global network of gravitational wave observatories have moved a step closer to detecting the faint radiation that could lead to important new discoveries in our universe. David Blair is a Winthrop Professor of Physics at the University of Australia and Director of the Australian International Gravitational Research Centre in Gingin. The team has announced a new measurement technique called quantum squeezing that allows gravitational wave detectors to increase their sensitivity. Gravity waves are ripples in space generated by extreme cosmic events, such as colliding stars, black holes, and supernova explosions, which carry vast amounts of energy at the speed of light. With the addition of quantum squeezing, physicists will be able to see much more distant sources and improve performances. Squeezed vacuum is injected into the dark part of the beam splitter to improve the performance of one of the detectors of the Laser Infrared Meter Gravitational Wave Observatory, which increase quantum noise. Gravitational wave detectors have been proven to be the most sensitive gravimetric instruments ever created. They measure motions measured in attometers, 1/1,000,000th of 1/1,000,000th of 1/1,000,000th of a meter. This will open up the gravitational wave spectrum and allow humanity for the first time to hear the myriad of gravitational sounds that are thought to be constantly rippling through space at the speed of light. Professor Dan Lee of Monash University and his team have designed a graphene-based supercapacitor, an energy storage system more compact than a conventional battery system. Endowed with an indefinite lifespan and ultra-fast recharge time, supercapacitors are well suited to energy systems used in high-drain charge environments, such as personal electronic devices, wind and solar plants, and electric vehicles. The challenge has been made to make SCs smaller, more portable, and to increase energy storage to volume ratios, also known as energy density. Supercapacitors are usually manufactured using porous carbon-containing an electrolyte liquid to transport the electric charge. The team substituted this traditional carbon structure with highly conductive and tensile graphene sheets, thereby maximizing space and vastly increasing energy density. An electrolyte liquid was then used to separate the sheets while conducting electricity with the superconductor. The Monash graphene-based supercapacitor has demonstrated an energy density of 60 watts per hour per liter, around 12 times higher than commercially available superconductors. Currently, this technology is at the stage of moving from the lab to commercial development. I'm Fallon Joslin for Nerd News, and see you nerds next week.